It is a pleasure to have with us Thimo Preis from the Institute of Theoretical Physics in Heidelberg, who will tell us about quantum systems far from equilibrium. Please.
Thank you. Well, thank you for the introduction. Thank you for having me. Thank you for the invitation. I'm very happy to be here and to talk about my work here today. I would like to talk about real-time dynamics and strongly correlated quantum systems far from equilibrium, which is generically a regime where it's very hard to come by first principles description. And in particular, emergent collective behavior can provide very important guiding principles. Here I listed some of the paradigmatic examples of such collective behavior. The most important one probably being the study of critical phenomena near second-order phase transitions in thermal equilibrium, where systems, after fine-tuning of relevant parameters such as the temperature, exhibit spatial scaling in their correlation functions, right, with universal scaling exponents and scaling functions. And the example I give here is of critical opalescence in a liquid-gas transition. This has led to a phenomena of different, such critical behavior near thermal equilibrium, which was then given a theoretical basis by this classification of Halperin and Hohenberg, which were able to group the different sets of scaling exponents and scaling functions into universality classes, which allowed us to, for critical phenomena of a very complicated system, to study the dynamics in the critical regime by a more simple system in the universality class. Other examples of such collective behavior are different low energy effective descriptions, such as hydrodynamics, where I show here a picture of turbulence. Right? Turbulence is a process, for example, energy turbulence, which describes how injection of energy at a certain length scale is redistributed to smaller length scales via the formation of eddies. And this has a prediction of to occur via a universal power law exponent and applies to very different systems. So this is a very turbulent, out of equilibrium, real-time process where we have some universal description which allows us to make progress in the LO description. On the side of dynamical systems, a very important concept is self-organized criticality, where it was proposed that dynamical systems, usually driven dissipative dynamical systems, run in their dynamics into attractor behavior, which is sort of quasi-stationary or stationary behavior being independent of the details of the initial conditions. The system runs into this attractor where the correlation functions exhibit power law behavior. And then you can make, again, universal statements. This has been found in earthquakes, in the study of avalanches of mountains, or in the spreading of diseases, or in the spreading of forest fires, where the number of burned trees is correlated with the area of trees that are burned. And this led to actually information of how one should deal with forest fires. Today, I would like to add one more item to this list. And these are universal scaling phenomena that occur in strongly correlated far from equilibrium quantum many-body systems, which we call non-thermal attractor and non-thermal fixed points. And they're associated, so these are quasi-stationary states. Think of an isolated quantum many-body system where you have very strong initial energy deposition, be it like fluctuations of strong fields, where the system will run into a quasi-stationary state where correlation functions exhibit scaling behavior with universal scaling exponents and scaling functions, which again allows us to formulate a notion of universality classes far from equilibrium. One example I give here is of a non-thermal attractor that is observed or discussed in ultra-relativistic heavy ion collisions, in particular in the first stage of the so-called bottom-up thermalization scenario proposed by Müller, Schiff, and Son, for the quark-gluon plasma. But the setting is that you have two, Lorentz contracted ultra-relativistic heavy nuclei colliding, going through each other, and then behind them they leave a very strongly interacting color fields. These color fields then decay via plasma-like instabilities and lead to the buildup of strong gluon-like gluon occupations. And the resulting system, which is strong gluon plasma at large energy density and rather weak coupling, is found to exhibit this self-similar scaling behavior, where this is, these are momenta perpendicular to the beam axis and parallel to the beam axis. These are simulations of classical statistical Young-Mills system in this over-occupied regime on the longitudinally expanding background, and one finds precisely that such a scaling is realized with analytically predicted exponents. Then you can also do a similar simulation for relativistic Bose gases, also on a longitudinal expanding Bjorken boost invariant background, and you find the same scaling exponents and the same scaling functions, like leading to this to this notion of universality far from equilibrium. However, at this stage, where this field is, or where this phenomena are discussed, is just we have observed them in very many different systems. So they are observed in inflaton dynamics for early universe cosmology, in heavy ion collisions, and in particular experimentally in ultracold atom gas systems. We have observed them and compared them between each other, but currently we are missing such a theoretical understanding and basis. So you might say, okay, this is all interesting that we find these phenomena, but why should I care? Why are they interesting? And I found that with this question, you're in the accompaniment of someone of the late Leo Kadanov, who, when asked about the relevance of scaling phenomena that were studied in the 90s, so-called fractals, also similar scaling behavior, said, where's the physics? And this was in an opinion piece for Physics Today in the 90s, where he said that further progress in this field depends upon establishing a more substantial theoretical base, in which geometrical form, so the scaling behavior, this universal scaling behavior, is deduced from the mechanisms that produce it. Without that underpinning, much of the work on fractals, read scaling here, seems somewhat superficial and even slightly pointless. It is too easy to perform computer simulations upon all kinds of models and compare the results with each other and with real-world outcomes. But without organizing principles, the field tends to decay into zoology of interesting specimens. So today I would like to make a step towards addressing this field and giving a more fundamental theoretical basis by putting forward this question. So how and why do these non-thermal attractors that we find across different systems, non-relativistic, relativistic, different field theories, how do they emerge in unitary dynamics? Right? This is always a question we also ask ourselves when we study thermalization of quantum field theories. With a unitarily evolving system, how do we actually lose sensitivity on the initial conditions? How does the system run into an attractor? And today I would like to address and answer this for this case of the non-thermal attractor. For the purpose of this talk, I want to first focus on an attractor that we experimentally observed in cold atom systems, and then in the second part, I will talk about the QCD attractor. Schematically, the setup is that we have an isolated quantum many-body system, and we want to study the real-time dynamics of it. Which is an initial value problem description where you have to specify some initial conditions. If these initial conditions are by some measure close to equilibrium, so near thermal distributions of particles or so, then you will simply observe relaxational dynamics, simply linear response regime. However, if you are by some way a notion far from equilibrium, which I here consider 2-point functions of being of order of 1 over the coupling, or 1-point functions being of order 1 over the square root of the coupling, so strong fields and strong fluctuations, we find that there's a wide range of of initial conditions which run into this non-thermal fixed point regime, where correlation functions now of different microscopic systems exhibit self-similar scaling behavior. And just to emphasize this, so this is different to critical phenomena because we don't fine-tune anything. Like we only need to go to this regime where we have to deposit a lot of energy, and it's weakly coupled, so it's an over-occupied weakly coupled phenomenon. But then anything goes. We can do, all couplings which are smaller than order 1, so to speak, all masses, different temperatures, and so on. And you will always end up with this regime with these scaling exponents. And the first system where this was experimentally realized was a cold atom gas experiment at Heidelberg University by the Oberthaler group, which I would like to walk you through here today. They prepare 60,000 rubidium-87 atoms in a quasi one-dimensional optical trap as a spin-1 Bose condensate. And what they then do is, so they prepare it in thermal equilibrium. It's a spin-up Bose condensate, so we have density-density and spin-spin interactions, and it's prepared in the M is equal to 0 sublevel of the F is equal to 1 hyperfine manifold of the spin interaction. And what they then do is they use microwave dressing to induce spin fluctuations. So you can go hopping to plus and minus 1 excitations, and this induces strong spin fluctuations, which quenches the system far from equilibrium. And then what they do is they study the thermalization dynamics. They now extract from the spin fluctuations that are being developed, so in the perpendicular plane to this one-dimensional trap, they then extract the notion of a 2-point correlation function of these spin fluctuations, which is plotted here against momenta for different times, early times, late times. And transiently, so not sustained, but transiently, they find that this self-similar scaling behavior is really realized, which is demonstrated on the right plot, where the distribution function here is rescaled with t to the minus alpha on the left side and then plotted against this combined variable t to the beta b. And you see that all the different curves collapse to a single curve, which corresponds to the scaling function. Here, interestingly, the scaling exponents, they are positive. Their values can be predicted, and their ratio is related to a conserved quantity. And the physics that is behind this is particle transport to the infrared. So an inverse particle cascade that emerges, where a macroscopic zero mode is being built up, so quasi-condensate far from equilibrium in a time-dependent scenario, which leads back to a superfluid-like description. What are the exponents? The exponents here are 1/2, both of them are 1/2. It turns out that in the system, so the particle number conservation leads to alpha is equal to d beta, so d is the spatial dimension, and d is 1 here in the spatial quasi one-dimensional system. And beta you can separately predict to be 1/2 for particle transport.
Just if I got the picture that you're putting there, so you're saying that these systems, there are some set of initial conditions that when we evolve, they will kind of converge to universal behavior, and they'll stay there for a very long time, but at the infinite time limit, they will go to their own.
Exactly.
So you're looking at this very long-lived fixed point.
Quasi-stationary state. Yeah, exactly. You can, in principle, sustain them forever, but then you need to pump the system. Because what you're doing is you're depositing an initial, large amount of energy, right, which somehow has to be redistributed to end up in a thermal distribution. And it turns out that the most efficient way is these type of cascades, inverse cascades and direct energy cascades that emerge. But they only sustain for so long that until the occupation becomes of thermal orders of order 1, and then the system simply thermalizes.
This is somehow very independent of the way that you initially distributed the energy in the system.
Yes, exactly. So it's as I said, so it's a wide range of initial conditions. You can think of choosing an initial condition which is somewhere like a Gaussian here or Gaussian here or whatever, and it will just spread towards the infrared into UV and lead to just a very efficient redistribution of the energy via different local transport of conserved quantities. This and here's like a demonstration of that these exponents are also sort of independent of the interaction strength. This is an experiment by Hadze-Babic group at Cambridge University, where they have a homogeneous Bose gas, and the interaction they can tune for the Feshbach resonance. So the S wave scattering length. So just think of this as the interaction parameter, and you really see that here, for very different values of this interaction parameter, you get the same exponents. It's rather universal.
It's at very late times, it has to also agree with the close to equilibrium statement, right? So does your scaling function has the property that it's for t much larger than p or something, it's for the argument very large.
So what happens at late times is that this scaling function is of course not realized anymore, right? The system departs from the scaling solution. So what will happen is that this part starts to come, so from the UV onwards, it starts to thermalize, and then it creeps into this, mode by mode, so to speak, that the the scaling function is, morphed into a thermal distribution. And so this is what has been realized in experiment. And now to understand theoretically what is really going on, we need a description, a model, which reproduces these results in our quantum analog simulator, so to speak. And what I want to talk about in the first half here is simply a ON vector model, a relativistic Mach vector model of n real scalar fields interacting with a quadratic self-interaction. We're then interested in, there's some labels in it. We're interested in the strongly correlated regime where propagators times vertices of order 1, so you need to resum a lot of diagrams in order to describe this phenomena. And what we use here is a next to leading order resummation in large N with Steven diagrams. So this is leading order, this next to leading order, and these are the resummation of the ring diagrams. And then we need a sort of framework which allows us to do real-time dynamics. These frameworks are very hard to come by due to the sign problem. For such scalar systems, there's a framework which basically is a generalization of the Kadanoff-Bain type equations you have in non-relativistic systems, which provide you with real-time evolution equations for the connected two-point correlation function. So here, this is the anti-commutator and the commutator of your fundamental Heidelberg fields. This is derived on the Schwinger-Keldysh closed time path. On the next slide, I have a short summary of how we do this. But let's say you have such a formalism available, which allows you to do real-time evolution from far from equilibrium to thermal equilibrium. The only thing you need to do is specify some initial conditions, where we here choose some over-occupied box initial conditions. So just put a box here, which is cut off at some hard scale Q, which has some large occupation, and then you just run the system. This just leads to a strong initial energy deposition and is very much non-thermal in the form. I also can tell you what the parameters here are, like for components such as in the Higgs factor, but it doesn't matter, different components, different couplings lead all to the same outcome. The evolution after some time is then shown here in the initial inset for the equal time statistical function, where blue is early times and red is later times plotted against momenta. And you see that, similar to here, such a self-similar power law behavior emerges where occupation fluctuations here are being transported to the infrared over time. And this is rescaled then here again. And the associated, conserved quantity that is associated to this is particle number conservation, which emerges in the infrared of the series. So this is a relativistic theory, but effectively non-relativistic in the infrared. Dispersion relations are effectively quadratic in the infrared, and particle numbers are effectively conserved, leading to these values for the scaling response. And then, this is a very nice comparison where this is our quantum analog simulator in the lab, and you see that we get the same curves and same scaling functions being realized.
Your model has a bunch of other conservations. Do they not matter?
They don't matter in the infrared regime.
Energy conservation, whatever, ON, charge conservation.
They matter, but they are not driving the dynamics. So what is essentially on a microscopic level happening here is that you have a huge increase in the rate of 2-to-2 scatterings, which leads to a buildup of an effective particle number conservation. You of course still have energy transport and so on, but these are all subleading simply in the effect. The energy transport will be more important in this regime at higher momenta, which I'm not showing here. There's a separate direct energy cascade, which is also realized here, which I'm not showing. And okay, so let me spend one slide on telling you how we do this, how we do these real-time simulations, as they're usually very hard. So we want to look at time evolution of an observable, which we do via Schwinger-Keldysh closed time path prescription, where you have to specify some initial state, some initial density matrix, and then you evolve by unitary evolution to the later state with your operator insertion and then back, which is this picture. And then so this is the time evolution contour, and then we need some equation of motion. This equation of motion is essentially provided by the Schwinger-Dyson equation for the propagator. It can be derived very conveniently from an effective action formalism, where you start from the Schwinger functional, you have a linear and bilinear source. Linear source usually gives you the field, right, conjugated after Legendre transformation for the one guy effective action. The bilinear source also gives you the resum propagator, and then an effective action extremal principle gives you equation of motion. But just think of the Schwinger-Dyson equation for the propagator, which is the full description. And usually, that in perturbative QFT description, you just expand this, right? You just take the self energy and you expand it in the free propagator. This does not work in real-time descriptions. Like then, your description will be some, set of diagrams where you have free propagators and then self energy insertions on them. However, this leads to the appearance of secular terms, which are terms where you have powers in the coupling and powers in time. And then, as you go to late times, these just blow up and your perturbative expansion is invalidated. What you instead have to do, and what we do here, is we solve this equation self-consistently, which you, for example, can also do, of course, in thermal equilibrium as a gap equation. We do it differently. We put this free inverse propagator, which is just a D'Alembert, box plus m squared usually, right, in coordinate space. Put it on the left-hand side of the propagator and let it act as a differential operator. And this equation is a differential equation which you can solve provided initial conditions. In practice, this is still the Keldysh contour, so it's a bit difficult to handle. What we do is we split this matrix, 2-to-2 matrix, into components, into the statistical function and spectral function, so the anti-commutator commutator, which splits this equation into two equations for these two, which are explicit in time and can be solved given initial conditions. And these are basically, generalizations of the Kelenoff-Bain equations. And so with this setup, we can then study the real-time dynamics. Now I want to address these two questions: how and why these attractors are approached in unitary quantum dynamics. For the first question, we recently understood how such attractors are approached. And what we did there is we looked for more general scaling ansatz. So instead of the scaling ansatz where you have t to the alpha here and t to the beta, we look for more general solutions which with time-dependent functions here, a of t and b of t, which you can use to introduce time-dependent scaling exponents. Similar, think of like temperature-dependent critical exponents near like a critical phase transition. And then as time, as these scaling exponents become constant, this just gives you a logarithm, and then this just reproduces the fixed point scaling. And it turns out very remarkably that you can actually plug this into the equation of motion and solve for these functions a of t and b of t. The solution is shown here, where in contrast to the fixed point scaling, you now have a resummation of an infinite resummation of power laws correcting the fixed point scaling. So it's just subleading and subleading power laws correcting onto the fixed point behavior. And that's very remarkable because it turns out that this completely describes the dynamics of this full quantum field theory nonlinear simulation. And this is what is shown in this plot, where I again show you this equal-time statistical function plotted against momenta, now times p squared. So it's just weighted differently, but it's the same data as before. And this sharp edge here is the remnant of the box initial condition that we use. So the blue lines are really basically initial times. And then what we do is we rescale this with the fixed point scaling exponents. And you see that this doesn't work at all, for all the times and so on, meaning that the system, of course, is not at the fixed point directly, right? It takes some time to go there. However, if you then rescale with this resummation of power laws, so really with this functional form here, you see that nearly all curves can be captured by this, meaning that after very short turbulent evolution of your quantum field theory simulation, like this is of the continuum description of your quantum field theory, the dynamics become very trivial. It's just a resummation of power laws which I can analytically give you. I think I find this pretty remarkable. And then you can recheck that the extracted behavior is really approaches the late time behavior as you continue in the time evolution. So this tells us that for this system that I'm discussing here, it turns out for different systems, the approach is a simple power law approach. There's a caveat for QCD, which I hope to discuss.
So here your analytic method is exact at large n?
Yeah.
Okay. And why do you need an ansatz? You can't just get this.
So what we do here, but we do next to leading order large n, right? At large n, so if you were to do large n, then you would only take this diagram into account. As the self energy, this is just a tadpole, and this just gives you a mass shift. Meaning it's a trivial theory, right? There's no scattering, no nothing. The system doesn't thermalize, it's just infinitely many conserved quantities, nothing happens. So you really have to go to next to leading order, and then we take all of these diagrams into account, and then you don't know the exact solution, right? But what you can do is you can plug this ansatz. I can say more about it if you're interested.
So it helps you find solve that kind of Schwinger Dyson type.
Yeah, what you can do is you plug this in, and then you can do a separation of variables. Turns out you can do the time evolution on the one side, and then this rescaled evolution on the other side, and the time evolution you can solve simply, which is pretty cool. And then you find that this is a solution.
And your expectation is that this universality class isn't different for infinite n theories and finite n theories?
No, I mean, because this is just the one simulation we do, but at the end we're comparing to the experiment, which is realized in different experiments. And this is just one setup. So usually these systems are not studied with these methods. Usually we do classical statistical simulations of Gross-Pedievsky theory, so of U1 theory, or also ON theories, which don't have these truncations. So here I'm just using the setup because this allows me in the end to do analytics to understand what is the mechanism behind it. But it has been observed before in classical statistical simulations where you don't understand, what is actually happening, but you don't have this truncation issue, so to speak. So this is the validation link. Okay. So now I want to talk about why an attractor emerges in unitary time evolution. And this we chose to explore by doing time-dependent linear response around the scaling solution. So again, the setup is, you evolve your quantum field theory, you see scaling behavior. The scaling behavior, with these positive exponents associated to Bose-Einstein quasi-condensation function equilibrium, and described by some scaling function exponents. Now what we want to do is, we want to add some perturbation and see how the system behaves. So we kick the system, we let it evolve to this fixed point, see scaling, we kick the system, add some atoms into it, shine some light into it, something, and then see whether the system decays and like it goes away from the fixed point, or whether it stays at the fixed. Is it stable or not? So probing the stability properties of this fixed point. Now that this is different to thermal equilibrium because we really are linearizing around this time-dependent background. And this is shown here in this plot where I now again show this data, but now plot it against time for two different infrared momenta. So the data that is shown here, the scaling solution is just these solid lines involving here. It's just two different momenta here and here. And then at a certain time, we kick the system. And we really, like in the simulation, I put some perturbation there. And then I see what happens. It's just one time. And we find that two different characteristic behaviors are realized. There's one which is decaying at higher momenta, which corresponds, of course, to stable perturbations, right? By this solution that the fixed point is stable. However, very surprisingly, there are momenta where the system is unstable. We see quasi-exponential growth away from the scaling solution. And this is was very surprising when we found this. It was on accident, basically, because this is realized, across different simulations for different microscopic models and different experimental systems. How can this be if there are unstable perturbations present in the system? And it turns out that these unstable perturbations correspond, so to speak, to the sensitivity to the initial conditions. And there's a self-stabilizing mechanism which makes these irrelevant in the time dynamics. And this I want to explain.
We looked at something like in the Atomov experiment. So
yeah, so this is what
in the Atomov vectors.
This is what we're sort of doing. We're computing the stability matrix. So I will show you the rate, which has some exponents, right? So it's just this on the quantum level for the correlation functions. To explain this, let me start off by talking about the quasi-particles, the degrees of freedom at this fixed point. And these we can extract from the spectral function. As I said, so the spectral function, we also has its own time evolution equation. We solve it together with the anticommutator. The two are related in thermal equilibrium, right, by fluctuation dissipation or KMS symmetry. Out of equilibrium, they're independent degrees of freedom. And then I can show you the spectral function. So this is frequency resolved here, Wigner transformed with respect to relative times for some time in the scaling regime, plotted against momenta, against frequency. It's anti-symmetric in frequency, so you can just focus on the positive frequencies. And then you see that, as indicated by these dashed lines, there are three different structures here present, which was also surprising because this is the structure you would expect, right? So this is just a scalar theory. So you would just expect a relativistic scalar field theory, just a delta peak shaped peak around the relativistic dispersion relation. However, what we found is that at this fixed point, there are additional dispersion relations popping up, the different peaks, which are just with dispersion relations which are just shifted from the relativistic one with ±2 times the effective mass. The effective masses are approximately constant here in this system. Note that if I were to continue running the simulation to the thermal equilibrium, these would go away. So this is really a property of the highly occupied system, that these are heightened. And they all turn out, they have sort of Breit-Wigner shape, and their widths actually scale to 0 as the system is at the fixed point, meaning that you get increasingly long-lived quasi-particles. And we found also that these quasi-particles that they appear has to do with the overoccupation that we get. So in the infrared we have this momentum dependence 1/p⁴, so which is huge. If you go to smaller momentum dependencies, it turns out that the spectral function really goes down, and you just have this one peak remaining. For physical picture, you can understand these actually. If you think again, so I said that we have a superfluid behavior, right, around this condensate, but now this is a quasi-condensate, it's time evolving. So in contrast to equilibrium, you really have like some, vector in your ON space, which is sort of rotating, right, and not with a fixed plane, but like just in the ON sphere. And then of course you have your Bogol-Lyubov and radial excitations around this condensate, but you also have all the other excitations which are parallel, like perpendicular to the plane spanned by this time evolving condensate. And these turn out to be these excitations, phase fluctuations. While if you look at magnitudes, here the peak seems to be very dominant, and these are very small. They turn out, especially this one here, turns out to be the dominant one driving the instabilities. And to describe this, we now use linear response theory, so we have this next to linear order time evolution equations, and then we plug in the scaling solution and linearize them in a perturbation with an additional gradient expansion time. And then you see that, and then we get an equation which predicts that the evolution of these perturbations is simply following some rate. Now, again, this is linear response around a time evolving background, and then the rate will also be time dependent. So this is very different to thermal linear response. And this rate we can obtain from the full next to leading order simulation, and it's shown here. So again, this frequency, momentum, and then this anti-symmetric, so just focus here. And you see again, there's 3 different structures and going up here. Now, however, they are all of the same magnitude, meaning that they are all very important, for the dynamics. And in particular, there's a pronounced negative region, which via this equation, you see that it leads to growing perturbations, right? And then the dominant contribution to these perturbations will come from the on-shell rate close to small momenta. And if you look at the on-shell rate, it turns out that these contributions, these negative contributions, are larger than the positive ones, and they turn this region negative, leading to these unstable perturbations. We have a physical understanding of why this negative rate appears. So again, if you continue the time evolution to thermal equilibrium, this goes away, this goes away, this all goes away, and you just see this one branch, which is just a stable thermal equilibrium decay, right? Stable thermal equilibrium. I will explain on the next slide why that is, but we find that the interpretation for why we have this negative region has to do with these new types of quasi-particles. That this positive branch, you can find an interpretation of just corresponding to 2 scatterings of your standard relativistic quasi-particles. While this negative branch involves a scattering process where you have this relativistic quasi-particle, your standard one, p squared plus m squared, and then one of these other ones, the omega minus ones, with this 2m minus omega dispersion relation, which basically leads to a sort of annihilation process where 2 condensate particles are being popped out. And this interestingly destabilizes the system. I can say a bit more about this. So this is a very full slide, so please don't be alarmed. I just want to show you that we have an expression for this rate. This can be derived. So there's some recipe of how to derive it from the next to leading order evolution equations. You do some gradient expansion, you introduce offshore occupation numbers, then you look at the scattering processes, and you linearize in the perturbations. And then you find that this rate is basically a linearized collision kernel in a Boltzmann-like description of shell, where you now have a sort of linearized gain loss structure and additional effective vertex elements, which you need because we have this strongly occupied scenario with 1/the coupling. And that's very interesting physics that emerges at this system, which I just wanted to highlight quickly. You can extract this vertex, which we have in our system because we do this large generous summation. And this vertex gives you an effective coupling, which decreases in the infrared, where we have this attractor behavior. Very strongly decreases. And this actually leads to a stabilization mechanism where you have this Bose enhancement leading to condensation far from equilibrium, shell by shell, more bosons are being created and transported. And when the vertex really becomes smaller and smaller and smaller as you go to smaller momenta, and this leads to a stable, so to speak, equilibration process. And then here, this is the same plot, but from the experiment, which is also pretty cool. But this is not the stabilization process that I mean. I talk about the stabilization of the fixed point itself. So we have this linear response formalism. One more step before I can give you the punchline. And this step is we have to quickly validate that this really describes the next leading order data. So what I'm showing you here is I integrated over time this evolution equation for the perturbation, which is now described by exponential of a rate. Now this rate is a rate integral. In thermal equilibrium, you have gamma minus ti. Here you integrate over the whole response from initial response to late time response, as it's a time evolving background. And Ti is the time where we apply the perturbation. And then this is the data that we get for the perturbation evolution in time for different infrared momenta. So the highly oscillatory signal is the next leading order data, so the full real-time evolution. And you see that the lowest lying modes, they all grow. And then as you increase the modes, as you go to higher momenta, you see that they decay quicker and quicker. And then these solid lines are the comparison with linear response. So this rate that we obtain from the simulation and then just can compare, saying that it describes the overall trend. It does not capture the oscillations because we use a gradient expansion, which means that we can use it to make a statement about the stability properties of this phenomenon. And This is the important slide here where we found the mechanism of, despite these unstable perturbations, the system actually becomes stable. So I said that the dynamics of the perturbations are described by this Andre rate integral. And since you have this time evolving background, the rate itself is time dependent and it scales also. And you can, I showed you an analytical form for this rate. You can just deduce the scaling from it because you know the scaling of the fundamental correlators. So this we predicted. And then this rate we can extract from the full next to leading order simulations. Here you see that, as you go to higher momenta, here these are, early times to late times, all in the scaling regime. As you go to higher momenta, you will find that the rate becomes increasingly positive, so increasingly stable by this equation, right? The higher you go in momentum. But then there's also a pronounced regime down here where perturbations are unstable and they grow away from the scaling solution. That these dynamics are self-similar is again, demonstrated by the usual procedure. We just rescale with these exponents, plot against the combined exponent. With beta, it's really here the same one as for the fundamental correlators, so it's a half. And you see that they all collapse to a single curve. And the single curve, which is the scaling function, we also find that we can fit it heuristically very easily with just this form. So it's just some non-universal parameters A and B, which are positive, and then this factor T to the beta B. And this is pretty remarkable because we have obtained our description, which allows us to make a statement about the late time behavior of these perturbations. Right? Does the system become unstable or not stable? Here we have basically obtained the stability matrix or the diagonal part of the stability matrix and the corresponding exponents from this. So pick your favorite momentum, which is unstable. So just take any one of these, right, which you would probe, and then you would see exponential growth. What turns out to happen is that, on a technical level, this rate turns positive after some time. You see this here, you pick some momentum for which the B is initially larger than this term here. And later times due to this additional power with beta being positive, this just outgrows the B and it becomes positive. And this you already see here, the whole construction, the whole rate is moving to smaller infrared momenta. Meaning that the one momentum that you probe, in time in your experiment, it will eventually show you something which is stable. And this is what we call a scaling instability, where this unstable regime in the rate scales to smaller momentum scales due to this quasi-particle inverse cascade. And then you can, from this counting, you can assign a characteristic time after which the mode that you're probing becomes stable. And this is a pretty remarkable mechanism because, so what you have, for example, these cold atom systems, of course, you have a finite box, right, that you set up your cold atom system in. And then imagine that you do some perturbation, shine some light into it, or add some atoms. What you will detect is that the system, after long enough times that you wait, you will always see something that is stable, right? In particular, the lowest lying mode is just finite because you have a finite box that you're considering. You're usually looking at the lattice system. And this leads to, like to the person from outside who is measuring things, detecting attractor properties, which is a sort of self-organized scaling mechanism. But I really want to emphasize that if you look into this inset, the rescaled rate is negative, right? This remains negative. If you continue to look in RG coordinates, so rescaled coordinates, your system is unstable. If you think of a temporal RG picture, then these attractors, these fixed points really have unstable directions, which of course they have to, because the system has to thermalize at some point and so on, right? This had to be quasi-stationary state. And this is, unitary dynamics. So something has to prevent it from just getting stuck there. So you have, in an RG picture, you have unstable directions. But the scaling itself is stabilizing the system and preventing it from going away from the fixed point for very long times.
You said inverse cascade.
Yeah.
It's energy, this cascading?
Particle number.
Particle number.
Yeah. And this is exactly this, moving of this rate to the infrared. This is going with this time beta, with T to the beta. Or characteristic momenta evolving with T to the minus beta. Right, and so this becomes, or this becomes order one. If here T to the minus beta, they are moving like this, meaning that this transport to the infrared. Which means that the whole rate, is moving to the infrared. So in momentum, if you don't look in rescale coordinates, so if you really think as an experimentalist, we're talking to the cold atom experimentalists at Heidelberg currently, and they're really thinking about what should I do to see this, right? So then they want to, add some atoms at some length scale, so always continuous, to see what happens. And, just from this picture, you will see that they will not see this, only if they have a large enough system and probe early enough times. So they would somehow, as an experimentalist, be, forced to work in rescaled coordinates, which you can of course not do, right? You have to somehow these rescaled coordinates relate time and momentum. It's very difficult to do in practice.
Can I take your word inverse cascade literally and ask you if you can write down a transfer equation across scales?
Yes.
Really like people doing turbulence.
Yes.
What would be the flux operator in this case?
So it's really it's the same picture as in turbulence.
There's mass, there's particle.
Yeah, it's particle number. It's particle number flux. So it's the only difference to turbulence is that our state is not stationary. We have a quasi-stationary state.
You're in 3D.
In 3+1, yeah, exactly.
So how do you get an inverse one?
So it's the particle number. Usually the picture in Kolmogorov is where you have a energy cascade in 3D and then inverse cascade in 2D, right?
Or in 3D, if you put something chiral, you could.
Sure. Also, here this inverse cascade really comes. It's not weak wave turbulence; it's strong wave turbulence. So really, you need these strong occupations, and you don't see it in the perturbative description. This is why this rate I showed. If you take this matrix element, this vertex event, then this just looks like 2-2-2 scattering, linearized 2-2-2 scattering. Then you won't see this effect. You really have to resum all of these interactions to see it. So this is just missed in the usual perturbative description, so to speak. And this concludes the first part of what I wanted to say about the stability of how the system stabilizes. And now I would move on to the attractor that you find in QCD and how it is approached.
Maybe just a question.
Yeah, please.
So what are the key ingredients? I mean, you wanted to have this emergent kind of particle conservation in the non-relativistic limits, but somehow could you have just put in, started with a field theory that had number conservation?
Yeah, sure.
Yeah. Okay.
So I don't think I have the paper here, but we did simulations where we do the relativistic ON and then the Gospodayevsky simulations, so relativistic and non-relativistic, and they have the same scaling function, same scaling exponents, same behavior. It's just on a technical level, I wanted to use the relativistic theory because there I can do manipulations in this framework, and the non-relativistic one is technically more difficult to implement in this functional form because you have a linear time derivative, and then just numerically it's not as stable. That's just a technical level.
And for the actual scaling functions, so presumably these exponents get 1/n corrections.
I mean, we are already next to the order 1/n.
Yeah, but the next. So
Yeah,
like
sure, next to the order, yeah.
Okay.
In principle, yes. But just again, so this formalism that I'm using is just for the sake of having analytical control.
Mm-hmm. So you're not quantitatively comparing it to experiments. You're just saying, this is a situation.
I mean, we have quantitative agreement, but I don't.
It shouldn't be, right? Because it's.
Yeah, I mean, this is not what I aim to do. I just try to understand what is going on. So what we use for quantitative agreement is classical statistical simulations, because this is a regime where we have a weak coupling and very strong occupations, and then classical statistical is exact, so to speak, because you really have the coupling going to 0+, and then you can do everything with field equations and just sampling. And this is where we have quantitative agreement with the experiment. And this is what people did for Gospodayevsky or relativistic systems, classical statistical simulations, and then compare it to experiment, and they find agreement. And then, I compare these simulations to classical statistical, find agreements by translation, so to speak. Yeah. But this is really for the insight, because such predictions I cannot write down on the classical statistical level. Yeah. Okay. So now I want to go back to this question of how the system approaches the attractor, because it turns out that in QCD there's a certain subtlety which does not appear in in Gospodayevsky theory and relativistic theory and scalar theories. And what I want to discuss here is an attractor. I will focus on the isotropic system, so I will not yet discuss longitudinal expanding heavy ion collisions, just for the just to illustrate the argument here. But you also find an attractor there. This attractor is characterized by energy conservation. So this is like a UV high hard scale. It's basically energy cascade, but time evolving phenomenon, where the exponents are now negative, meaning that you have transport of energy to the UV, to larger momenta, smaller distances. And the occupations are now large, but not strongly correlated large. And then we describe this by doing QCD kinetic theory simulations. So, the formalism proposed by Arnold Moore and Jaffe with just effective 2-2 and 1-2 processes. And it turns out that scaling is broken in the system. So we thought for a long time that you have clean non-thermal attractor that is realized in the classic QCD simulations. However, if you look very closely, it turns out that it's a very technical thing in the 2-2 collision kernel. In the scattering matrix element, there is a contribution which is time dependent. It comes from the electric screening mass, the Debye mass, which is there because it's the leading thermal correction to the scattering process, and it has to be included to regularize unphysical divergences. And this is time dependent. You cannot extract it out, and this prevents you from doing a separation of variables where you have a scaling and something which is not scaling, which is just in this rescale coordinates. And this is demonstrated in these plots here, where we did QCD kinetic theory simulations, starting from largely over-occupied states with some recoupling. G squared is 10⁻⁴ or 10⁻⁵, 6 or so, and then some large occupation here. And here I show simulations with the 2-2 plus 1-2 kernel, and then only with 1-2. And this is the distribution function shown in the insets, which is p squared, and then again, as before, I rescale this distribution function with the analytical exponents. And you see with the full collision kernel, this doesn't work. So this is really a precise plot where you can really see that it doesn't work, so to speak. If you were to look a bit, if you wouldn't look as closely, you would see it looks kind of fine, but you really look closely. And then with the 1-2 collision kernel, it works remarkably well over 6 orders of magnitude in the time evolution. And we wanted to understand, what does this actually do to the scaling? Do we still have scaling? What is the phenomenology? What happens in these weakly coupled, highly energetic gluonic plasma, quark-gluonic plasma far from equilibrium? And it turns out that this is a bit more difficult to analyze than in this large N scalar case, just because of this Debye mass, because it's not, you cannot extract it and pull it out of the collision kernel. And so what we did is to make a statement, even at least a qualitative one, is we made a small angle approximation. So we approximated the collision kernel with a Fokker-Planck form. I'm not showing you the detailed form because it doesn't matter. It's just important that this approximation, which just says that small angle scatterings dominate, which is the statement of, for which is the paradigm of the bottom-up thermalization scenario. It turns out that in this approximation, the Debye mass is simply factorized in front. And then I can again make statements about these scaling evolutions of the scaling exponents. And you really see here, so this is what I get for the 1-2 kernel, this is for the 2-2 kernel. So you really see that there's like a logarithmic correction to it, which now prevents me from writing down an analytical solution, a close analytical solution. So I get like an equation now, which I have to solve numerically. And this I can compare now with the full QCD kinetic theory simulations. Here, we did very extensive simulations over 8 orders of magnitude for a very long time. This is of course not as, in a heavy ion collision, this is not as sustained, right? But we wanted to study really what is precisely going on in this regime. And then different colors here correspond to extracting the scaling exponent from different moments of the distribution function. And what you see here is that, over 8 orders of magnitude, there's still like a rather large gap compared to the analytical value. And this is the dashed line is the analytical value. The black dashed curve here is then the solution of the numerical equation. You see that it at least qualitatively follows rather closely this prediction. So we wanted to use it to make a statement about what these corrections in QCD make of the non-thermal attractor, whether it is relevant or not, and what happens of the physics here.
Is this in some large N approximation, or is this N
no?
= 3?
This is just N color is equal to 3. This is the standard Arnold Moore QCD kinetic theory with LPM resummation in the 1-2 and then 2-2 effective scatterings. And it turns out, so this equation you can solve at late times in an expansion in logarithms and logarithms of logarithms. So this is this expansion. We find that you can self-consistently solve this. Remember that for the scalar case, we found just power laws. So in that language, in comparison to logarithms, these are very fast degrees of freedom and a fast approach. Here we find at late times, so there are also power laws here, but at these late times, it's just logarithms left. And there's an interesting behavior where we actually find that these coefficients also grow factorially. So you have like a transient structure with a vanishing radius of convergence. which is interesting of itself. But physically, what is most relevant is the late time correction here, which is just 1 over log. So it's a 1 over log correction. And then we compared this prediction to the, again, QCD kinetic theory simulations, where we start from different initial conditions. So these are, different initial box heights and different, Gaussians, boxes, different forms of the initial conditions. All are like large energy depositions, and all with different couplings and so on, just to probe the universality. And then you find that all these different initial conditions converge into a late time behavior, which is captured by this logarithmic correction. There's a
just to understand. So the approximation is in kinetic theory, you're truncating. I guess you're linearizing.
Yeah.
Kinetic theory. Okay.
Yeah.
Maybe to go back to this, at finite n, that's a reasonable thing to do at large n, but not in general.
Yeah. Okay. I understand what you're saying.
In that sense.
And then you can, and then for us, this was very interesting. There's an interesting analogy or similarity to discussions of hydrodynamic attractors that are also very commonplace in heavy ion collisions, which are predicted from the strong coupling holography side, where an hydrodynamic attractor describes the late time evolution of your energy momentum tensor of matter undergoing this longitudinal boost invariant expansion. And there you have also a notion of fast with the slow modes. So there you have non-hydrodynamic modes, which come from transient excitations, and hydrodynamic modes, which are slow, which are just the hydrodynamic evolutions. And then these, fast modes decay, and then at some point they are gone, and then just your description is hydrodynamic in the usual second-order relativistic hydrodynamic sense. And here we also have such a separation of scales with different modes, so fast modes and slow modes, and this trans-series structure. So it's very interesting to us whether one can draw an analogy, because these attractors one finds in the weak coupling limit of QCD, like evolution in the quark-gluon plasma, and then these hydroattractor you find in the strong coupling regime. So maybe there's like some transient state you can understand these two away, like in the physical limit, which is of course in between the two. Okay, then last but not least, I talked a lot about how systems approach such attractors and how they stabilize themselves. And then you can of course ask the question, how does it go away from it to thermal equilibrium? And this just as a parametric estimate. As I said, this happens when the overoccupied regime ends. So when the occupations become of order 1, this you can just make an estimate. And the typical hard scale of the system, when does it become of order 1? And this is just given by the strong coupling or power of the strong coupling, given by the inverse alpha scaling exponent here. And then with this late time correction, you can estimate what is the deviation of the exponent at the system at the time when the system should thermalize from the fixed point value, to estimate how close it is to the fixed point actually. And it turns out that even for these recouplings that we are using here, you still have percentage deviations from the fixed point, meaning that in this QCD case, the attractor is really a weak coupling limit, and it in more realistic scenarios where the coupling is really stronger, the system spends most of its time simply pre-scaling. So it does develop such a time-dependent form with pre-scaling exponents, but it doesn't really go to the attractor, and then probably goes to the next stage of the thermalization scenario. And with this, I would like to come to my summary and give an outlook. So I try to highlight that we have these non-thermal attractors that we find in different systems. We find it in early universe cosmology, cold atom systems, and heavy ion collisions. And I wanted to understand, what is the theoretical base behind them? Why do we find them? How do we find them? How are they approached? And for the how, we found recently that as I said, we have these power law fast approach in most systems, and then in QCD you have these very interesting scaling breaking dynamics which lead to logarithmic corrections. And this similarity between hydroattractors and the weak coupling attractors really led us to I would like to understand how do you transition between the two. So one is the strong coupling limit, the other is a weak coupling limit, and whether in heavy ion collisions you maybe realize one of the two or go from one to the other. Because the weak coupling one is an early time attractor, the strong coupling one is a late time attractor. Can you maybe sort of translate between the two? And in particular, we formulate the dynamics of these weak coupling attractor in terms of these time evolving pre-scaling exponents as slow degrees of freedom, and one can somehow map them to the hydrodynamic fields in their evolution, just as in degrees of freedom. And then as to the why, the question was why does a system under unitary dynamics approach an attractor? How does it lose sensitivity to its initial conditions? And here we found a mechanism, this scaling instability, where you really can understand that the unstable regime is a sensitivity to the initial conditions. The unstable perturbations are, the unitary dynamics that would drive you away from the attractor. But then the scaling behavior itself makes them sort of less relevant in time, and renders the non-thermal attractor dynamically attractive for like a characteristic time for each mode that you are probing. Meaning that you still have these, you don't lose, of course, you don't lose dependence on the initial conditions because it's unitary dynamics, but you effectively lose it, right? This dependence is encoded in these unstable perturbations which grow, but in the end, they don't matter. It's just that this overwhelming inverse particle cascade just sweeps over everything and just, coherently propagates and correlates through the system to build up the condensate. And this demonstrates from first principle a mechanism how such attractor behavior, so quasi-stationary state in the unitary evolution, effective loss on the details on the initial conditions, can be realized from unitary dynamics, even though we have unstable directions. And you don't need to fine-tune, which is what we call self-organized scaling. And this for us is a very interesting mechanism because it really, for the first time for us, illustrated how you can approach such an attractor in a dynamical quantum many-body system. And we would like to understand, does this like translate to different self-organized attractors that you find in different, quantum many-body systems? And maybe is this a step towards finding these universality classes that we find in practice, but have not been able to define the low energy effective theory from. Where as a last point, what is really interesting also here is our collaboration that you have with experimental groups, that they can realize a remarkable degree of control in their ultracold atom systems, and then you can use them as quantum analog simulators for the attractive behavior that you maybe get in QCD, and it's very hard to study. So you can just do the cold atom system simulation and learn something in this universal regime. Where we're interested now, in particular, in learning about all of this phenomenology, so studying the perturbations and these pre-scaling dynamics as the system is approaching the attractor. And with this, I hope I gave you some ideas of what the physics is in these scaling phenomena, and thank you for your attention.
Any questions?
Can I poke you again on the turbulence there? Did you show us the power spectrum for that?
No, I haven't. Okay, I have some backup slides where I can explain it. Okay. Okay, so this is turbulence. This is turbulence.
You seem unusually prepared. Maybe you can. Do you have also scaling arguments for the power?
Yes.
Spectrum?
Yes. Unusually prepared. So this is just a slide on how usually turbulence works, right? So you look for a stationary solution, which is just a power law. And then you have some Boltzmann description, you plug this in, and then you relook for solutions where the collision kernel vanishes. And this power law exponent can then be determined, you just plug this into the collision kernel, you get some overall scaling that you can plug out, which is this, okay? It's just some number. And then the exponent is determined by the relevant conservation rule, which is here, which I here write energy conservation, but you can just take away this omega here, and then you have particle number conservation. And then what has to be conserved is the flux, right? Is this A, or this A which we define the momentum dependent flux, which has to be independent of the scale that you are probing. So you really have to have a power law behavior. And some arguments follow, and then what essentially you find is that the exponent is given really by this has to be 0. And then you can, solve this and find this exponent, which gives you the energy cascade for Kolmogorov. Or if you here plug in a particle number, it will be just, 5 or 4, for the inverse particle cascade. Now, what we do in practice, what we do in practice is sort of similar. We don't look for zeros of the collision kernel. We look for, such general solutions of the distribution function. And you can again plug this into the Boltzmann equation. Then on the left-hand side, so your derivative acts on this, so just isotropic homogeneous system, just one time derivative, acts on this, takes down an alpha, and then acts on the internal one, gets a beta. But you can just pull out a t to the alpha minus 1. And then on the right-hand side, you again plug this into collision kernel and can rescale everything and pull something out. And this gives you one scaling relation for these exponents, which is just, this exponent which is here is alpha minus 1. And then what is really happening is determined again by conservation laws. And on a practical level, we do this a posteriori. Like we see something, some scaling exponents, and we check, this quantity in the relativistic system and find that it becomes a constant. And then say, okay, particle number is conserved. What would this mean? This means, so you plug this ansatz in here, you get alpha minus 3 beta or minus d beta from the phase space measure, which gives you this scaling relation. Or energy is plus z, and z is the dispersion relation coefficient. And then you have two equations which you can solve as soon as you know the collision kernel. And that's how it works in practice. And then, we know the collision kernel for the different systems, and then we get these three halves and 1/2, or minus 4/7, minus 1/7, and so on.
And the summary is in that graphical, the slide. Very fast.
This one, right?
Yeah, exactly.
Yeah. So this is the dynamics of non-thermal fixed dynamics that you have in isolated quantum like scalar systems. Okay, not expanding, just like box. And what you have is, so think again of the initial condition is some energy deposition at some hard scale. It can be at some box initial conditions, but for example, in inflaton dynamics, you have a very strong inflaton field, which is some scale somewhere, and then it decays and builds up fluctuations from there. But okay, let's say you have some hard scale here, where the energy is dominated of the system, and then what happens is you have both these cascades which go direct and indirect. And this has to do with in an isotropic system, these conservation laws of energy and particle number conservation cannot be fulfilled in the same momentum range. So what we in practice do is we look for a solution to the scaling relation in one momentum range and one in the other momentum range. So in this hard scale regime, this direct cascade regime where the distribution function is sort of perturbative, we see that you have evolution to the UV, meaning that you have negative exponents, and then with particle number with energy conservation, you find these exponents. In the IR, we observe particle number conservation and positive exponents by the same argument. You find 3/2 and 1/2. And what is basically, so this you can already get basically from a Kolmogorov like analysis. If you just take perturbative 2-to-2 scattering and plug in this ansatz, you just have to do it for the ansatz. But this you cannot get. So this is like, so to speak, an old story. But this is the new story where you have to, because occupations are large, you have a strongly correlated system, you cannot use perturbative diagrammatics also. And this is why we needed this next to a large n summation. And then really the exponents that you get from the collision kernel change, and they change then these values, which we then found to agree with the experiment, so to speak. That's the logic. And you effectively have a source and a sink building up in the system. So usually Kolmogorov power law is you have ejection of an energy here, and then energy cascade goes down to some sink somewhere, right? And this you drive, and then it just continues forever. What we have is it's an isolated system where you have energy deposition here, and then you have an effective sink here and an effective sink here, which is being developed. So like some bumps, basically where the energy is transferred. These are, that there's like these characteristic momentum scale, and they go in both like directions. So that, in the end, what you will have is this will be Kolmogorov, and this will be Kolmogorov. So this will be 5 Hertz. This will be 1 over p to the 4th. But then you also have this new piece, which has to do with this time evolving behavior. Okay.
The cascade is local in K.
Yeah.
I wonder if you can write a Crunchman type of formula. And instead of putting the eddy turnover time that will give you Kolmogorov, you put some characteristic time scale of your process and pull out an informal argument that justifies your.
Maybe, yeah, we can try.
Because that relies only on locality in K.
That's true.
That's miraculous argument.
Yeah. Happy to discuss, yeah.
Okay, let's thank Thimo again for.
So